Hi guys, welcome to a lesson of ordinary differential equations. So in the previous class, we discussed about the Riccati's equation and so we concluded first order differential equations and some classical classification of differential equations. Now, in this class, we are going to talk about some mathematical models that arises due to changes in the quantities, right? So we will talk about some mathematical models, more precisely deterministic models. So now the question is how these differential equations arise, right? So as we mentioned in the earlier classes, that differential equations arise when relevant physical laws and principles are applied to a problem, right? So by considering infinitesimal changes in the variables of interest, we can say that, for instance, we know that velocity is equals to change in the displacement with respect to the change in time, right? So therefore, we can obtain the governing differential equation for a specific problem and requires an adequate knowledge of the nature of the problem or the phenomena. So the variables involved, appropriate simplifying assumptions and the applicable physical laws and principles involved, right? So now let's talk about some uh, heat exchange phenomena. So that is Newton's law of cooling, right? Law of cooling. Now we know that if we take a hot body to a cold or uh, body where temperature is lesser than that of the hot body, then the hot body is going to transfer the energy or heat energy to the atmosphere and going to be stabilized at the room temperature, right? So we know that this phenomena because we know that the heat flows from higher concentration to lower concentration. Okay, so Newton's law of cooling says that the heat flow is equals to H times A times T naught minus T. Now we will describe what these things means, what these elements, these notations means, right? So Q is simply the rate of heat transfer, rate of heat transfer. So consider that we can see a phenomena that a small solid ball of some mass m and with some radius is at some initial temperature. Let's say the temperature we can say as T1 equals alpha degree centigrade, its initial temperature of the ball, and that is dropped into a large container filled with hot water at some temperature, say T hot or T naught, that is 70 degrees centigrade, or that is beta degrees centigrade. Let's say that that is beta degrees centigrade, where beta is greater than the alpha, right? So cold body, a cold body is immersed into a hot body, right? So now what will happen? So eventually this cold body is going to gain some temperature from the hot body, right? So the temperature of the cold body is going to rise. So therefore, uh, the temperature of body in general varies with the location within the body as well as time, right? The object can be assumed to be the same at every point at the given time, and the temperature of the ball under consideration can be considered to be a function of time only. Now we know from the experience that a cool object left in the warmer environment gradually warms up. That is a physical phenomena, and that is very clear, right? So now this heat transfer phenomena is given by this expression written here. This expression, that is rate of heat transfer is equals to HA times T naught minus TA, or we can simply say this is directly proportional to this difference of these temperatures, right? And where H times A is the constant of proportionality, so we can write uh, uh, KHAHA times T naught minus T. Okay, so this is, and where A is the area, surface area of the material, say ball, surface area of the ball, of the ball. And H is nothing but the coefficient of heat transfer. It's the coefficient of heat transfer. Okay, and T, we already talked about T, that is the temperature of the ball, that is initial temperature. T, sorry, no, not initial. Initial temperature is other thing. Temperature of the ball at any time T, temperature of the ball at any time T. And T naught is the temperature of the environment, or we can say it's the ambient temperature, environment, or the room temperature, or whatever, right? So the conservation of energy principle. Now, the conservation, we know that the conservation of the energy principle says that energy can neither be created nor be destroyed, but it can be transferred from one form to another form, right? So we know that the increase in energy, increase, now increase in energy of the ball during the time delta T is going to be equal to total heat transfer. Total heat transfer. Now we can see that how that expression comes here into the ball, during this time delta T. Right. So far so good, right? So now we know that we can write increase in the energy. For this we have a formula, that is MC delta T. From our previous physics classes, we know that Q equals MC delta T, that is the heat energy, right? Q is the heat energy, and it's equals to MC delta T, and that will be equals to total heat transfer into the ball during the time delta T, right? So this is time that is represented by delta T, and this is also time represented by delta T. So MC delta T is going to be equal to HA times T naught minus T. Okay, that's fine. That's fine. Then if we divide this expression by delta T on both sides, what happens? delta. Sorry, one thing I missed here. It's not delta T, it's actually delta T. That's change in temperature, MC delta T. My mistake. It's MC delta T, not change in time, it's change in temperature. So MC delta T. Now we can divide this expression by the change in time, that is delta T, small t. So delta T over this will be simply uh, one thing that is missed here is delta T. It's also delta T because it's the total heat energy transferred to the ball during the time. So it's HA times T naught minus T times delta T over delta T. Now we can see that this delta T and delta T cancels out, and this MC we can move on the right side to the denominator. So on the left side we will have delta T over delta small t equals HA over MC times T naught minus T. So now we, by simplifying this equation as taking the limit delta t tends to 0, it will give us dt over the small t, that is the instantaneous change, and HA over MC times T naught minus T. So for this HA over MC, we can take it as lambda, that is constant, so we can take it as lambda. So the Newton's law of cooling is in its very simplified form, and this is the Newton's law of cooling, right? So if a problem is asked like for instance that for example you can consider that you take a cup of hot coffee. Let's say here we can just make a question that if you take a cup of coffee initially at let's say 80 degrees to an environment where temperature is say 30 degrees. Now what will happen? Eventually, this cup of coffee is going to lose some energy, heat energy, and going to like decrease the temperature, right? If you take a cup of coffee initially at 80 degrees centigrade to an environment where temperature is 30 degrees centigrade, and say this HA over MC, that is, we already discussed that H is the heat transfer coefficient between the ball and the environment, A is the surface area of the ball, or there we talk about ball, but here it's cup of coffee. So we can like uh, have these constants. So M is the mass and C is the specific heat. So let's say if it's given like it's 0.8 for instance, right? So it's say it's 0.8. So the equation we will have is dt over dt equals, now this is actually lambda, right? So we can write 0.8 times T naught. Now what's T naught? It's simply the room temperature minus T, the temperature of the coffee at any time T, right? So now we can see that this is a simple separable differential equation, or we can solve it as by making it a linear differential equation as well. So it's up to us. So we can see that it's dt over dt small t, and we can move this 0.8t to the right side, and 0.8 times 80, 0.8 times 80. Okay, and so now this is a linear differential equation, so we can find the integrating factor by using this formula. So the integrating factor is 0.8t. Right, so the differential equation will be t 0.8t, and we are very much familiar with this stuff now. So it will be t e to the power 0.8t integral 0.8 times 80 times e to the power 0.8t dt. So now this will be t e to the power 0.8t equals 80 times e to the power 0.8t, because after integration this 0.8 and this 0.8 will cancel out, because you know that the integral of exponential is the exponential itself, and then in the division the derivative of the power, right? And plus, we'll see here. So it will be t equals at plus c e to the power negative 0.8t. Now see here this negative sign, which shows that the temperature is going to decrease, right? Now we need to find c. So the initial condition is given that the uh, coffee mug is coffee is 80 degrees centigrade initially, so we can plug in the values here. So it will be plus c e to the power 0, or uh, it seems that there is some mistake here. Let's see. Okay, the mistake is there that the room temperature is not 80, it was 30 degrees, so it's a blunder here. Let's correct it. This was 30. So, hmm, so you can see that the room temperature was 30, but we write it mistakenly, so it will be 30 here as well. So it will be 30, 30. And the initial temperature we have is 80. So now it's fine. This implies that C equals 50 degree centigrade. All right. So now we can write T equals 30 plus 50 times e to the power negative 0.8t. So we can see that every time the temperature is going to decrease, because this exponential power is negative. So let's say what happens if t tends to infinity. So the temperature is going to be 30 plus 50 times e to the power negative infinity, which means that this will become 0 and t equals 30 degrees centigrade. So we can see that the cup of coffee is going to be stable at the room temperature. That's perfect. That seems logical. That makes sense. And that's all for the time being for today. You can practice these kind of problems. In the next class, we'll come with some other laws. We will talk about Lambert's law. We'll talk about population models, decay models, and we can talk about chemical reactions and all this stuff. So thanks for watching the video. That's all for the time being. Thank you.